Okay, so let's go and pick up from where we had previously. We talked about the problems trying to solve this equation using boundary layer theory, and now let's try and fix this using WKB theory. So WKB theory is really based on some mathematics from Green. And I'm giving Green a shout out because he's from Nottinghamshire and that's where I'm from. So WKB theory. So WKB theory wasn't invented by Green, but it comes from how we handle essential singularities. Now we've talked previously that if we had a regular singularity, we try a solution it's like the Frobenius series. So for regular singularity, we try y twiddles t to the r. Now if we have an essential singularity, basically that's happening because you've got something that's exploding worse than a polynomial. Right, so regular singularity means you're getting a polynomial, so you're getting something like, I don't know, t to the minus 1. An essential singularity means you've got something that explodes worse than that. It's often an exponential, so you try y twiddles e to the at of r. I know this isn't a lecture notes going through some examples using essential singularities, but I'm going to skip over it today because we're short on time to some extent, and you don't actually need to know it for WKB theory, but it is a very useful tool in mathematics if you are going to go and further your career doing it. Some of the really difficult problems, it's good to know how to tackle them. It really does help you out. But we're not going to do that today. We're just going to borrow the idea from here, and that's this throw an exponential in there. So the way that WKB theory works, so let's just cancel this. Sorry, my office light is going dark. Obviously my office doesn't think I'm moving enough. Right. So the way that we're going to sort this is, let's just put a line across here. We're going to borrow this idea. And the whole idea behind WKB theory is, let's go across to here. We want to try y twiddles e to the s over delta, where delta is small. Okay, and then once we've done this, we basically swap y for s, and then we want to solve for s. So and our default way of trying to solve these problems is to use an RPE. So we try the RPE s twiddles s naught plus delta s1 plus dot 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 dot. So plus delta squared s2 plus dot 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 dot. Okay? So this is it. This is WKB theory. We can do this approach and we can make quite a lot of progress. So let's go for the problem we had. So we had epsilon y double dash plus y equals 0. And I'll throw in the boundary conditions. What was it? Y of 0 is 0, y of 1 equals 1. So if we do this, what are we going to get? So I want to basically replace my y with e to the s over delta. And to do that, I need to differentiate it, right? And we need to, so we want to replace y with e to the s over delta. So I need to differentiate this. So thinking about how you differentiate e to the t squared, that would be 2t e to the t squared, right? So thinking about how you do that, with this we're just going to get y dash is s dash over delta, and that's e to the s over delta. And if we do y double dash, if we do the product rule, we're going to get s double dash over delta plus s dash squared over delta squared. And I'm aware that my s's and my deltas are kind of similar, so we'll see how we get on. S over delta. If they're really joined up, it's a delta. If it's not so joined up, it's an s. There we go. Okay. So this is just using our product rule, etc., on differentiating this. So if we get hold of this and throw it into this equation, we have epsilon. If you want to pause the video, you can do, right, to work out these calculations in between steps. Anyway, we're going to grab this and we're going to throw it into here. So we're going to get epsilon, and it's going to be s double dash over delta plus s dash squared over delta squared, e to the s over delta, plus, and y is just s over delta, right? And that equals 0. And you'll notice that both of these terms have an s over delta, so we can just go and cancel them out. So in that case, we're just going to have epsilon s double dash over delta plus epsilon divided by delta squared s dash squared plus 1 equals 0. And now what we want to do is we want to find delta. Right. And the way we're going to do that is we're going to do the method of dominant balance. So I somehow want to get these terms so they can balance each other. And the trick to notice here is I've got these two terms here, and this first term, I'm going to write the order symbol. And if we look at it, we've got an epsilon over delta here. And I'm going to go to this term here. I'm going to write order. I'm going to have epsilon over delta squared. And I'm just going to get to this one here. I'm going to do order and 1. Now they can do the thing where we try and balance every single thing. And it makes it, you can do it, but it's a bit slow. So the way to do this quite quickly, because we're getting a bit better at asymptotics, is to actually just inspect these two and have a little discussion with yourself. And this one here, I notice I've got epsilon over delta, and this one I've got epsilon over delta squared. And I know, given delta is a small number, that no matter what I do, this one is always going to be the bigger one. This is always going to be bigger than that because I'm dividing by delta squared, right? This is always going to be the larger one. So this thing here is always larger than that. So there's no way this can balance this term. These two cannot balance each other because this one's bigger. So this has got to be balanced out by the 1. So the way that this goes is I need to have epsilon over delta squared must be equal to 1. So delta must be equal to epsilon to the half. Okay, so a really important thing when you do your WKB theory, when we're doing it, is basically, this is how I described it in class, so it might be easy to follow. So I'm just going to write down, we can ignore s prime prime compared to s prime squared to find delta. Okay, so maybe that's an easier way of thinking about it. So if we go back to our equation, this s prime prime, this second derivative, is always going to be smaller than s prime squared. So if I did that and I go back to my equation, we've got s prime squared over delta squared plus 1, we've got an epsilon there, equals 0. And the only way to get this to work is if epsilon equals delta squared. So this bit here is 1. So that means delta is epsilon to the half. Okay. So that's the only way I can get it to go. So we've got what delta is. So we know what delta is. And just like all these other problems, once you know what delta is, you want to go back and you want to substitute it into the equation, right? So let's substitute delta is epsilon a half into this. Okay, so if I do that, we're going to have epsilon over epsilon a half, s double prime plus epsilon over epsilon a half squared, s prime squared plus 1 equals 0. And we can just rewrite this out. We're going to get s prime squared plus 1 plus epsilon a half s double prime equals 0. And then now we can actually just solve this using an RPE. And we even said at the start, the RPE we want to use is this thing. So we can get hold of that. We now know what delta is, right? Let's just go across to here. So I like changing colours. It makes it look exciting. So using S twiddles S naught. Now delta, we said was epsilon a half, S1 plus dot 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 dot. We can solve this problem. Now something I forgot to say, so I'm going to go back and make sure, I'm going to write at the start, is whenever we do this, I've not actually said what we're trying to solve for exactly. So what we want to do is we want to find a leading order. And when you find a leading order with WKB theory, because of the exponential, and if you have a look in the lecture notes, we talked about exponentials and asymptotics and how it's a little dodgy. But to make it nice and simple, I'm just going to say we need the first. So normally if we're trying to find leading order, we only need one term. But with how exponentials work, we're actually going to need the first two terms for S. And the reason why is you can only stop, so this is the bit I want you to know, is this bit. But if you're wanting to understand why that's the case, the reason why is if you've got an exponential and some sort of asymptotic series, I don't know, A1 plus A2 plus A3, you can only stop this at leading order. So if AN is little order 1. So basically your asymptotic series has to stop when the term tends to 0. Okay, so this isn't a bit in the lecture notes about exponentials. I think there's some homework questions about can you take the exponential of both of these two sides. So go and look that up and investigate that if you want to figure out why we need two terms, okay? But it's basically you have to stop, you can only stop the asymptotic series once everything is little over 1. But don't worry about this too much for now. We're just going to say we need the two terms. But again, if you really want to pester it, come and speak to me. Or, sorry, if you want to, not pester it, that's a wrong terminology. If you want to go and figure out why, come and speak to me in class or outside of class or whatever. And go and look up the bit on exponentials. Right. I'm waffling, so let's get back to the problem at hand. So we're going to use this, and if we look on this equation here, we can work out what S prime is going to be. That's going to twiddle S naught prime. Now I've talked in the past about not differentiating asymptotic series. We're not going to worry about that right now. We're going to have S double prime, and that's just going to be S naught double prime. That's S1 double prime, etc. Okay. So we're going to grab this and we're going to throw it into this equation. And if I do that, we're going to get S prime squared, so that's going to be S naught prime, plus s1 prime, epsilon a half s1 prime squared plus, I think we had a 1, and then we had an epsilon a half, and then it was s prime prime, so that's s naught prime prime plus, I'm going to write dot 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 dot, and that equals 0. And when we expand this term, we're just going to get an s naught prime plus 2 epsilon a half s naught prime s1 prime plus dot 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 dot. We're going to get a plus 1, and we're going to get an epsilon a half s naught prime prime is 0. And this is just the stuff we've done in the past, right? Now we're just collecting powers. So order 1, we're going to get s naught prime, there should be a squared there, s naught prime squared plus 1 is 0. That's from all the order 1 stuff. If we look at order epsilon to the half, we're going to get this term, so we're going to get a 2 s naught prime s1 prime, and we're going to get over here, we're going to get an s naught double prime equals 0. Okay, so let's solve this first equation. So if we solve this first one, let's go across. So we're going to find, pardon me, we're going to get s naught prime squared is minus 1. So that means that s naught is going to be square root of minus 1, which is going to be I. So we're going to get plus or minus I. Okay, so I've got s naught prime, and then I can integrate that to find s naught. So s naught is going to be plus or minus it. Now normally we would have a constant, but I'm going to say we don't need a constant. You can stick it in there if you want, but we don't need it. So the best trick most of the time is to set it equal to 0. There are some times when it's better to not set it 0, but most of the time we will set it to be 0. Okay, so let's do, so we've got our s naught here, let's try and find s1. So here we're going to have 2 times s naught prime. Well, we know s naught prime is plus or minus I. We're going to have an s1 prime, and we're going to get an s naught double prime. If I differentiate I, I'm just going to get 0. So this whole thing equals 0. Okay, so that's that bit. And so here, so if we look at this, we're going to have s1 prime is 0. So that means that s1, so normally we'd say it's equal to a constant, but this advice still applies. So we might as well set it equal to 0. Okay, so here we have it. We've got s0 and we've got s1. And we want to use that to solve, remember we're trying to solve this differential equation. And we tell ourselves that this is a second order differential equation. So normally that means, well, not normally, that means that there's going to be 2 separate solutions, right? So normally it's like a to the 3t plus b to the t, right? We want to have 2 solutions. And we currently have y twiddles, what did we say? E to the s over delta. Now you'll notice that we actually have 2 values of s, right? Here we have 2 values, and that is going to be how we get the 2 different solutions. We're going to use these 2 values to make our 2 different answers. So let's see how we do this. So we're going to have y is going to twiddle, so we're going to write a plus, and that means I'm going to use the positive one. Okay, so it's going to be e to the plus I t. this is all over delta, right? So this is S naught, plus delta, and then it's times by S1, so that's 0. And we're going to get A minus E. I'm going to stick in my other S naught, so my first one was plus IT, my next one is minus IT, plus delta times S1. Now my S1 was 0. And that's all divided by delta. So we can kind of neaten this up a bit, and we're going to get A plus E. So we can ignore this 0. We're going to get IT. We know delta is epsilon a half. And we're going to get A minus E to the minus IT over epsilon a half. Okay, we can actually finish off the problem now by applying our boundary conditions. So I'm going to go over this kind of quickly, but if you want to do y0 is 0, that is going to tell you A plus equals minus A minus. And if you want to do y of 1 is 1, that is going to tell you that A plus is going to be 1 over e to the I over epsilon a half minus e to the minus I over epsilon a half. Okay, so I've gone over those very quickly. If you want to have a crack at doing that, go for it. So that means that my final answer is going to be e to the IT over epsilon a half minus e to the minus IT over epsilon a half, all over this stuff. Okay, so that is my final answer, but we can simplify it a little bit. So we can use the fact, I think we might have used this before in a lecture, so we can use the fact that sine of u, 2i times sine of u is e to the u minus e to the minus u. And we can use this to make this a little bit nicer. So if we do that, you can write this top bit as 2i sine of t over epsilon a half divided by 2i sine of 1 over epsilon a half. And that is what we're left with. And this is actually, it's not only, this is the exact answer. Sorry, I just got a bit tired there, so my brain went for a second. So in fact, this has actually given us the exact answer in this case. But we're going to do another example in a second, where we can use it to solve a much harder problem than the one we've just done. Okay.